In most of my videos, I assume that the viewer has a little basic electronics knowledge, and in general, I kind of aim these at a person with the equivalent of a junior or senior level EE student. In other words, someone that has had basic circuits and the electronics and things of that sort, and is now prepared to move on to actually working with the circuits and using them to do some simple things and also some complicated things. But in this video, I'm going to change gears. I'm going to assume that this is someone, a viewer, who does not have any basic electronics training except fundamental familiarity with what a transistor is and things like Ohm's law, which relates the current and voltage to the resistance in a circuit. So I'm going to use the circuit on the left to demonstrate how, with nothing more than knowledge of Ohm's law, you can first design transistor circuits. And as we get a little further along in this, I'll show you how you can cascade these so that you can have a multiple transistor circuit. But for right now, we're going to stick with a single transistor. I'm also going to assume that you can also afford a $20 multimeter. The multimeter you see on the right is this one from Tenma, which costs $20.99, checked on the internet this morning. This is a relatively low-cost meter that I bought, and it works fairly well. There are hundreds of multimeters online, so pick the one that you like and the one that you think gives you the best value. But I'm going to use this one. One of the first things that you need to do is to pick the transistor you're going to use. Now, the reality is this circuit will work with virtually any transistor. But in my particular case, I've chosen an NPN transistor. The NPN transistor determines two things. One is how the currents flow through the transistor and the polarity of the voltage source. In this case, the voltage source is positive relative to ground. But except for that, the transistor you choose doesn't really matter. I've chosen a fairly inexpensive 3904. And you'll notice here that this is the pinout of the 3904 that I chose. Notice that pin 2 is in the middle. 1 and 3 are on the sides. Over here is the diagram. Now, what that means is that the base is pin 2. That's in the middle. The emitter is pin 1. That's on one side, and the collector on the other. So what I've done is I've inserted a 3904 in this tester. I'm now going to turn it to the HFE position, and you'll notice that it displays about 250. Now I'm going to do something here just to illustrate that this is not a hard and fast number. Every transistor will be a little different, but watch what happens when I heat it up by putting my fingers on the transistor. Obviously, if this were in a heated enclosure, it would change much faster. My point is that HFE is just a number. HFE is basically the current gain of this transistor. And the reason I show this early is you want to make sure you have a good transistor, and one way to make sure you have a good transistor is to plug it into a tester like this that has an HFE measurement and see what the HFE is. Now, as we'll see in a minute, the HFE is not guaranteed to be 250 like it is in this transistor. But we're going to first take a look at the characteristics of the 3904 that you can get off of the data sheet, and then we're going to set about designing the circuit that you see. By designing, I mean choosing the values for the emitter resistor, the collector resistor, R1 and R2. We're going to choose those values based on Ohm's law. So let's look at the spec sheet for the 3904. Here is the data sheet for the 3904, which you can obtain online for free. You can download it. And what I've done is I've printed out a portion of the second page of the data sheet because this is the one that we're going to start with. And what we're interested in is this DC current gain chart. Now you may notice that it's for two different transistors. The top one is the 03 and the bottom one is the 04. We're interested in the 04. It gives several different rows for current gain, but the one we're interested in is the one here that shows a minimum and a maximum. You notice it shows a minimum of 100 and a maximum of 300. The reason we're interested in that is we want to know what was the test current. It was 10 milliamps DC with a voltage from collector to emitter of 1 volt. So we're going to choose 10 milliamps just as a working figure. And once again, just like the HFE, these are all just estimates at this point. I'll call them approximations. So the first thing we're going to do is choose a value for this emitter resistor. Now we just saw on the data sheet that we want to use about 10 milliamps. Let's assume that we want about 1 volt at this point. That means that with 10 milliamps flowing through the resistor, once again this is just Ohm's law, is voltage over current, which in this case is 0.01 amps or 10 milliamps. Well, E is 1 volt. We want about 100 ohms. Now when I say about, this is exact. 1 divided by 0.01 is exactly 100. But 100 ohms is a value we can use right out of the box. It's a standard value. But we may come to some values here that are not standard values, in which case we're going to want to choose the nearest standard value. So we're going to make this 100 ohms. The next thing we're going to do is choose the load resistor. Now for reasons that we won't get into until later, I want this stage to have a gain of about 10. For it to have a gain of 10, that means that this resistor has to be about 10 times this resistor. This resistor is 100 ohms, so this is 10 times 100 or 1,000 ohms, sometimes written as 1K ohm. Okay, this is where we're going to take our output from, so this is sometimes called the load resistor, or RL instead of RC, but we'll stick with this terminology for now. You may also notice that if you've seen other circuits, often this resistor is bypassed with a capacitor. We're not going to do that, and we'll show that later, because what I want to do is use this to illustrate not just how you might design a common emitter amplifier, that is an amplifier where you put the input into the base and you take the output from the collector, and the common is the emitter. But also, if you want to design an emitter follower. So for example, you might want to take the output from this point. The input's the base, the output is the emitter. And you can use the same circuit to do that. So, okay, we've decided on this resistor and this resistor, and we know that we have about 1 volt here. Well, the next thing we need to figure out is how do we go about choosing these resistors? Well, the first thing we want to do is we want to figure out what the voltage is at this point. We know it's a volt here, so if we can figure out how much voltage there is across the transistor from base to emitter. And let me draw in those letters. This is the base, this is the collector, this is the emitter. So it's the base to emitter voltage that we're trying to determine. Well, we can look on the data sheet for that. But a better way, I think, is just to measure it with our meter. After all, we paid a huge $20 for this meter. We might as well get lots of use out of it. So let's set that up and I'll show you how you do that. As you recall from the data sheet, if you turn the flat side of the transistor towards you, then the emitter is pin 1, the pin on the left. So what I have now done is I've connected the positive lead of my multimeter, that is the red lead to the base, and the black lead to the emitter. You see that over here. It's a little hard to see. Now I've turned the meter to the diode test position. You notice it has a little diode symbol. And you see the figure that it reads is 0.652. What that is telling us is that the base to emitter voltage on this transistor is approximately 0.65. Just because it doesn't really matter, we're going to round that up to 0.7, partly just to make our math a little easier to do. Once again, these are all just approximate numbers. The exact values don't matter. So 0.7 volts is the base to emitter voltage. So we've determined that the voltage from base to emitter is 0.7 volts. Well, the emitter is already 1 volt. That means the base is going to be about 1.7 volts. In other words, we just add those two up. Now, with 1 volt here and 1.7 volts there, we're now going to try to decide how to choose the values of R1 and R2. We're going to pick R1 so that, given our supply voltage, we can supply about 10 times the required base current to this transistor. So, okay, that sounds pretty complicated. How in the world do we do that? Well, we talked a little bit ago about HFE. For this transistor, we're assuming that HFE is about 250. But we saw on the data sheet that it can be as low as 100 and as high as 300. So what's HFE? Well, it's just a complicated term for the gain, the current gain of this transistor. The current gain means if I put in 1 milliamp into the base and the gain is 100, that 100 milliamps will flow in the collector. That's the current gain. It's what the relationship between the base current and the collector current. Well, another thing that you need to understand about transistors is, in normal operation, what's called linear operation, the collector current and the emitter current are essentially the same. Now, there will be a small amount of base current that adds to the emitter current, but don't worry about that. For our purposes, we're going to say the emitter current and the collector current are identical. Well, we already know what the emitter current is. It's 10 milliamps. That means there's also 10 milliamps flowing through this resistor, the collector resistor. Well, 10 milliamps through 1,000 ohms is going to produce a 10 volt drop. So we're going to write that here, 10 volts, and we're going to do it like this with little arrows to show that that's across that resistor. Okay, if there's 10 volts across this resistor and 1 volt across this, that's a total of 11 volts. We need a little bit of voltage across the transistor. Let's assume that we're going to use about 4 volts across the transistor. 1 volt plus 4 volts plus 10 volts is 15 volts. And that's how we determine our supply voltage. So now we know we have a 15 volt supply, and we want to determine R1. Well, the way we do that is by assuming that the base current is related to the emitter current by the current gain. Well, we're going to assume for now we're going to use the minimum value, and we do that for reasons of margins in the circuit. But for right now, we're just going to assume for this purpose that the current gain is 100. That means that the current flowing in the emitter is 100 times the current flowing in the base. So if we take the current flowing in the emitter and we divide by 100, we will get the base current. However, for our design purposes, we're going to choose a total current flowing through this resistor of 10 times the base current. And we'll talk about that later when we talk about stability. So, instead of dividing this by 100, we're only going to divide it by 10 to determine the emitter current by 10 to determine the current through this resistor. 10 milliamps divided by 10 is 1 milliamp. Now we want something that will drop 15 volts down to 1.7 volts with 1 milliamp flowing through it. So let's calculate that. So I've drawn the current of 0.001 amps flowing down through this resistor, and since we have 15 volts at the top and we have 1.7 volts here, that means we have a total of 13.3 volts across the resistor with a current of 0.001. Once again, R equals E over I. So let's calculate that, and I've done so on the calculator, and you'll see it's simply 13,300 ohms. Well, we're going to round that up. You can't really easily buy a 13,300 ohm resistor. So we're going to round that up to 15,000 ohms, or another way to write that is 15K. So R1 is now 15K. So we've determined RE, RC, and R1. Now let's determine R2. Well, remember I said there's 0.001 amps flowing down here. A small amount will flow into the base, and the rest, that is 90% or more, will flow through this resistor to ground. For our purposes, remember we're just using approximations. We're now going to try to determine, okay, if there's 1.7 volts here and 0 volts down here, and what is the approximate current flowing through this resistor? Well, for our purposes, we're just going to use this same 0.001. In other words, we're going to assume that no current flows into the base. Everything that flows down here flows straight through here. We know that's not quite right, but it's close enough for us. So we want 1.7 volts across a resistor that has 0.001 amps flowing through it. So let's calculate that. 1.7 over 0.001 gives us 1700. Well, once again, we're not going to use 1700. That's not a standard value. In this case, we're going to round that down to 1500, which is 1.5K. So we've determined RE, R2, RC, and R1. That's everything we need. We also now know approximately what our voltages should be. We should have about 1.7 volts on the base, about 1 volt on the emitter. We should have about 10 volts across this resistor, and we should have the difference, that is 15 minus 10 minus 1, or 15 minus 11, or 4 volts across this transistor. That's called the collector to emitter voltage. So VCE is about 4 volts. So now let's build up that little circuit and see what we actually get. Remember, for this purpose, we chose an HFE of 100, but we know our transistor is really around 250, so we know these numbers are going to be off, but it doesn't really matter, as you'll see. I put together the circuit on this breadboard, and don't worry about all the extra parts on here. The only extra parts are these capacitors here, 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 and one up there. I'll talk about those a little bit later. The transistor is right in there behind that capacitor. Turn this so you can see it a little better. But what we're interested in is we determined that there was going to be about 10 volts across this resistor, and we'd like to know whether that turned out to be true in our circuit. We know it's not going to be exactly 10 volts because we know our transistor has higher current gain than what we assumed. So I have hooked up a power supply. You'll notice on the bottom it shows the current, which is about 0.01 amps or 10 milliamps, and I've set it a little higher than I wanted to. I'm going to drop it back to about 15 volts. We've hooked our meter up with the negative lead, or the black lead, on ground, and the positive lead on the collector. So let's see what we got in terms of voltage. Well, we got 8.6 volts. So now let's take a look at the emitter and see what it's producing. I moved the test lead over to the emitter. We have a 100 ohm emitter resistor. And what's our emitter current? If you move the decimal point on the meter to the left 2 places, you get 0.00687, which is 6.87 milliamps. So what we have verified is that this transistor is operating about where we expected it to. We have established a workable bias point. In the next part, what we're going to do is actually look at how this amplifier amplifies. Remember, we said we adjusted the collector resistor to be about 10 times the emitter resistor. That is, this resistor is about 1,000 ohms. This resistor about 100. 1,000 divided by 100 is 10. So we're going to expect a gain of about 10 from this stage. Once again, it's just approximate. Let's see if we can measure that. I've connected up the analog discovery 2 to the circuit. Channel 1 is set up to 100 millivolts per division, and channel 2 is set up to 1 volt per division. Why did I do that? Well, remember what we were looking for. We're looking for a gain of approximately 10. 100 millivolts is 1/10 of a volt. You see that these are approximately the same, which means that the input is about 10% of the output, or another way to put it is, the input is being multiplied by about 10. Now we can also see that we have approximately 180 degrees of phase reversal between the input and the output. Not exact, but approximately. What does this tell us? Well, for one thing, we have a working circuit. It has a gain of about 10. It is biased about where we thought it would be. But the most important thing to learn about this is that you can design transistor circuits, at least to a first approximation, with nothing more than Ohm's law. You can measure them, at least for their DC performance, with a simple $20 multimeter. Now, it is very helpful if you also have access to some kind of waveform generator and oscilloscope so that you can test the circuit dynamically. But we're going to talk more about that in part 2, which is going to be more about feedback. In the meantime, we're using the Analog Discovery 2, and as I always say, I don't have anything to do with Digilant, who produced this, in terms of any kind of relationship. I think they're a good company. I did buy this Analog Discovery 2 using the educational discount. So in case you're wondering, did they give me this? The answer is no. I paid what any other person using this for academic purposes would do. And I don't have any commercial purposes. I'm completely retired. So I hope that you've enjoyed this part 1 on the transistor amplifier basics. In part 2, we're going to talk a little more about things like frequency response and feedback. In the meantime, have a nice day.